Hey folks, this is Major Jones here to talk to you about how we can take that state diagram that we introduced in the last lesson and actually build a digital logic circuit that implements that state machine. We'll start with, this is the state diagram from the last lesson. So this is describing that little 4-button combination lock. And I'm going to make just one kind of addition before we launch into the lesson, which is to say I'm going to I'm going to number each of these bubbles. I'm going to give each of these states a number. So I'm going to start with 0. I'll increment. I'll do 1, 2, 3, and then 4, just to kind of number these circles, because that's going to be critical for us to get to a circuit. Okay, so we know it's not purely combinational logic that is implementing this thing, because whether or not a C unlocks my device, it depends on which state I'm in, right? It does if I'm in my state number 3 right here, right, ADB. But it doesn't unlock my system if I'm in basically any other state. But what I want you to see, now that we've got state numbers, is that there are parts to this system which do start to look like combinational logic. For instance, we'll start with my output values here. I already kind of said that the only finite state machines we're going to look at in this class are ones where the outputs have specific values based on the state. So if you can imagine for a second that I've got a part of my circuit which can tell me the state that I'm in, right? The binary value of the state that I'm in. Then I could pretty easily come up with a truth table that unambiguously tells me, based on my state, what's my output value. And it's only in this last state, 1, 0, 0, where my unlock signal is true, and I don't really need much of a truth table to figure this out based on the way I've numbered this thing, right? If the value my state value has a 0 in the most significant bit, then I'm in states 0, 1, 2, or 3, and my output is 0. And it's only when I have a 1 in this most significant position that my output's true. So the truth table is pretty easy. If there's a 0 here, it doesn't matter what's in the lower positions, then I'm not unlocked. And if there is, then I am unlocked. So this is unambiguously combinational logic, which is a good step forward. As long as I have my state, I can design combinational logic that tells me unambiguously what my outputs are. That's piece number 1. Number 2, I want us to look at just a couple of transitions, a little subsection of the state diagram here. So we'll take a look at this first portion here, where I'm in sort of my reset or my default state, where no correct buttons have been detected. And you'll notice kind of from this diagram, right? If I detect A, I advance 1 state. If I don't, then I just stay where I am, right? Okay, so here's that little kind of snippet. If there's an A, then I move here. If there's not, then I move here. Again, let's assume that we have a part of our system which is telling us the current state, right? The current state for this one here is 0, 0, 0. So I can list for each of my states, each of my inputs, which in this case I only really care about A, and based on those 2 values, I can unambiguously write down what my next state should be. So these 2 lines are telling me if I'm in this no detected state, 0, 0, 0, and I don't have an A, regardless of what B and C and D are doing, then my next state, which is called Q prime, is 0. I stay in the 0, 0, 0 state. But if I'm in this state and I detect an A, regardless of what B and C and D are doing, then I advance to the next state, A, which we gave the number 0, 0, 1. And that's true unambiguously every time. So again, this is combinational logic. If I have my current state and I have my inputs, I can write a truth table. I can design combinational logic that tells me what my next state should be. So what I'm starting to see here is that I've got I can basically start to kind of formulate my finite state machine in this fashion. I've got, we started with number 1, kind of this little bubble right here, right? It said if I've got my current state, so in this case I've got 3 bits that determine my current state. If I know what my current state is, I can unambiguously design some combinational logic that tells me what my output should be. And if I have my current state, so you can see that this current state value kind of wraps around here. If I have my current state value, which are these 3 bits, and I know my 4 inputs, then again, this second little exercise shows me I can unambiguously define what the sort of next state should be, what state the finite state machine should transition to. And again, we use Qs typically to refer to the variable that's the current state, and Q prime to talk about sort of the state that's next in time. So Q prime is my next state. And this is my finite state machine. The only piece that I need to figure out is this piece in the middle of my circuit that tells me my state. And the things I know about this part of my circuit so far are that it basically has to kind of remember the value of this state between inputs, and I want to set it up in such a way that that I can give it a new value on the input that it automatically remembers sort of on the next increment, the next clock cycle or something like that. And furthermore, lastly, I want to make sure that this whatever this piece of circuitry is, that it is kind of synchronized to a clock edge, and because otherwise I get some weird feedback loops. And what that should all start describing to you is the D flip-flop. All I need to implement my state is one D flip-flop for each bit of my state, and so then that becomes a part of my circuit. I can use these three values, Q0, Q1, Q2, literally the Qs, the outputs of these 3D flip-flops, to determine to go into the combinational logic that describes the output, potentially more than one, but although in this example there's just one, for my finite state machine. I can take each of those 3 bits and wrap them back around and define little blocks of combinational logic with my inputs that describe what the next value should be in these D flip-flops. And so this is a circuit which defines my finite state machine. All I needed to do, I started with sort of the state diagram here, right? That kind of behaviorally described what I wanted this finite state machine to do. And then all I needed to do were create 2 little truth tables. We'll call these effectively state tables, or at least this one's called a state table because we're talking about current versus next state, that described what I wanted the outputs of my system to be based on my inputs, what I wanted the next state of my system to be based on the current state and the inputs. So let's show you an example. Let's take a look at an example of how we might take a state diagram and work ourselves to a complete state table. Right? This is a state machine that is it doesn't have any context right now. It's a do nothing state machine, just purely for example purposes. And you can see I've got 3 states here. Okay, 0, 0, 0, 1, 1, 0. I've got one output y, which is 0 in my 0, 0 state. It's a 1 in my 0, 1 state, and it's a 0 again in my 1, 0 state. And we'll assume that this state machine has 2 inputs, A and B. Right? I want you to take note of 2 things. One is that we'll assume that based on the underlying system, A and B cannot both be true at the same time. Like maybe this is like a slide switch, right? It's either in one position or the other. It's never in both. So we'll use that because we'll see state machines in the future that have that feature, and I want to show you how to handle that in the table. And you'll also notice that there's no state 1, 1. We could have a state 1, 1 because we have 2 bits, but we don't. This state machine, I've got a couple of transitions here, all kind of color coded to show you how we're going to start filling out this state table. Okay, so to fill this out, what I can do is I can write 2 tables. Right, I've got one table for my output, which is just based purely on my inputs, and I've got a separate state table that describes what my next state is going to be. The way I like to do this is to list my states on the left, my current state values on the left, followed by my inputs. And what that allows me to do then is sort of plant myself mentally in this 0, 0 state, because that corresponds to these first 4 rows in my state table. And then ask myself, okay, based on every combination of inputs I see here, where do I go next? All right. So if I'm in this 0, 0 state, what I see are sort of 3 arrows, 3 outbound arrows, right? I've got the A not B arrow, which stays here, says I loop back around to the 0, 0 state. I got the not A not B arrow that says I go to the 0, 1 state. and I've got the not A, B arrow that says I go to the 1, 0 state. So you can see here kind of color coded. If I'm in 0, 0 and A is 0, B is 0, that means I'm in the first row of my truth table or my state table. Then my next state is 0, 1 because that's where this little kind of light blue arrow is taking me. All right. If I'm in state 0, 0 and A and B are 0, 1, that corresponds to this arrow here, then my next state is 1, 0. So that's what I write here in my next state. And if I'm in 0, 0 and A and B are 1, 0, then I stay in my 0, 0 state. So these three arrows are defined here in the first three rows of my truth or my state table. We'll deal with this fourth row in just a sec because you can see here it's based on my first note. It's got a bit of an illegal input combination. And so we'll handle that in just a sec. All right, you'll notice now if I move to the next state, 0, 1, I've got one arrow that corresponds to A, not B. I've got another arrow that corresponds to not A, X. I've got an X here to indicate a don't care. So this one term defines both not A, not B, and not A, B. Right? You can see that kind of in these first two blue rows of this portion of the state table, that this arrow kind of covers both terms. And you might see that occasionally in state diagrams. You might say, in this state, I'm going to go here if not A, or if A is 0, and it doesn't matter what B is doing. And so I've got the don't care here just to be very clear in this transition that I'm saying I don't care what B is. Remember that in order to accurately define this state diagram, I have to fully describe what happens on every input combination. All right, and so sometimes I'll need a don't care to sort of capture multiple rows in my state table. And then here we see again that sort of one or always transition, which covers basically all of my other inputs. And so that's sort of the next state logic or the next state table. My output pretty clearly based on just these three states is 0, 1, 0. So you can see that here. But again, I've got sort of an unknown. I'm not sure what to do in state 1, 1 because based on my note here, there is no state 1, 1. All right. So this example should model a lot of the state machines you'll see in this class. If it happens that you've got like an input combination that's not possible or a state that doesn't exist, then basically what we can do is put don't cares for those sections of the truth table, right? So if I'm in state 0, 0 and A is 1 and B is 1, in my state table at least I still need to kind of define what this is, but if I know that that's not a possibility, then what I can do is put a don't care here. And that helps me definitely when I go to describing my logic because like at this point when I've got some don't cares in my state table or my truth table, that makes the K-map a lot easier potentially, or simplifies it, right? So if I've got an input combination that doesn't make sense, I can put don't cares in my next state. If I've got a state that doesn't exist at all, then I can put a don't care in my output, and I can also put don't cares in my next state because that's just never, my state machine should never find itself in that state. So the don't cares in this case I can use to my advantage to help simplify the logic. Now an alternate kind of option might be to use a 0 in place of these don't cares. And in fact, if I were doing this for real life, like I would probably do that just to be kind of on the safe side, right? The idea is, let's say, weird stuff happens, right? So maybe my state machine, it is in state 0, 0, and even though it should never happen that A and B are true at the same time, maybe there's a little glitch or some noise, and my state machine does think that A and B, are true. In that case, these don't cares, these don't really exist in the digital circuit, right? Like when I reduce this K-map, these are either 0 or 1 based on the resulting logic, the things that I've circled. And so in a real case, in the totally, unlikely scenario that my state machine thinks it's in this row of my truth table, if I have the don't cares here, then, maybe it takes a weird transition. It starts to go places in my finite state machine that I didn't really intend it to go. So for in real life, to be safe, what maybe I say in this scenario, okay, let's just force it back to 0, 0. We'll sort of start over again. In the hopes that maybe that was just a glitch and we'll kind of start over. Similarly for like my output here, the output if y equals 1, conceivably that's like kind of turning on something. And so if my finite state machine ever thinks that it's in state 1, which is totally wrong, but maybe there was a glitch or some noise or something that got me there, this if there's a don't care, just like before, then that's going to be a 0 or 1 based on my digital logic circuit. Maybe that's not what I want to have happen. Maybe I'm using this finite state machine to turn on some piece of high powered machinery. And a 0 here would be maybe a safer option. So that's an alternate here. Instead of a don't care, we could potentially put zeros. And in real life, that's probably what I would do to kind of keep things err on the side of safety. But in this class, it's totally fine to put the don't cares because that'll definitely simplify the converting these two tables into digital logic. Okay, so that's how we take a finite state machine diagram like this and convert it into an actual circuit, or at least a state table, which we can define with combinational logic blocks. At this point, it should be pretty clear to you how to take something like these tables here and convert them into combinational logic using Carnot maps. We'll see an example of that in the next lesson, kind of top to bottom, how we take a finite state machine problem and produce the digital logic circuit that implements that device. That's all I got, folks. See you next time.